I welcome you all in this course on power plant engineering. Today we will discuss about the photovoltaic conversion. We will start topic to be covered in this lecture are first of all we will introduce what is photovoltaic conversion, advantages of photovoltaic conversion, description and principle of working of a photovoltaic conversion device that is known as solar cell, maximum conversion efficiency, to what conversion efficiency we can go for, and we will name some describe certain common solar cells. Okay. So, starting with the introduction, the photovoltaic conversion this photovoltaic conversion, why it is called conversion? It is called conversion, photovoltaic conversion, because the solar energy which is falling on a surface is converted to electrical signal or electrical energy. So, that is why it is called photovoltaic, or it works on the photovoltaic effect. And it is another way of trapping the solar energy. One is the solar thermal energy, solar thermal systems which can tap the solar energy. Another is photovoltaic conversion of PV, photovoltaic system for trapping the solar energy. And these systems are becoming very popular nowadays because they are direct conversion systems, and the energy which is falling on the photovoltaic cell is directly converted into the DC, and this DC can be used for running different appliances. And you must have seen in the cities, in the rooftops, there are certain panels which are laid, and the array of the panels facing a particular direction. These panels, they contain PV cells, right? And output of the panels is adjusted in such a way that we get desired voltage and current at the output, and this desired voltage and current output, either we run the DC machines, right? Then DC fans are also available nowadays. So, we can run the DC machines directly from them, or we can send this energy to the main grid, but when we are sending this energy to the main grid, the losses are high. Third option is we can store this energy and then charge the batteries and use the batteries for different applications, right? They have no moving part. The beauty is no moving part. Little maintenance is required. You have to clean, only keep the surface clean, PV surface clean, otherwise the efficiency of the cell will go down drastically. And the best part of it, that it takes the diffuse radiations also. If you look at the solar thermal type of system, they work on the direct radiations, beam radiations. They don't take diffuse radiations, or they take diffuse radiations, but the percentage is very insignificant. But here they take the diffuse radiations also. You must have seen the calculator which are running with the solar cell. They don't require batteries, right? And you can operate those calculators sitting in a room. And the rooms, we are getting only diffuse radiations. We are not getting direct radiations. So, that is the advantage of these type of devices, that they can take the diffuse radiation. And for different power requirement, you can simply adopt these devices. Just changing the arrangement, the connections in an array, you can have different combinations of voltage and currents. So, that is also in favor of the PV devices. The main disadvantage is they are costly. And because nowadays the companies are going for the mass production, so the cost is also coming down to a reasonable limit, and the government, in past the government was also giving subsidy on these devices, PV devices, right? So, different governments are giving the subsidy on these devices. So, in all, this is a very neat system for power generation, but still it is a non-conventional source. It cannot be used as a base load power system. So, this does not pollute, it is cheap, versatile, and load factor is very high, 85 to 90% is a load factor for this type of devices. Now, description and the principle of working. Now, there is a crystal, single silicon crystal, single crystal silicon cell. So, there is a wafer of single crystal. the entire crystal we will not take. We take a wafer of a crystal of 0.2 mm thickness, maybe of 0.2, just to give you an idea, 0.25 mm thickness, we say 250 microns, right. Now, on the bottom side, because top side is facing the sun, so bottom side it is covered with the metal, there is a metallic cover, right. On the top side, there is a fogged cover, because if we completely cover the top side, then where the sun ray will fall. So, the top side cover is a fork type of cover, just to hold the wafer on the surface, right. So, it has a junction, there is a P junction and N junction. So, junction is formed here. The thickness of this junction is approximately 0.2 micron, very thin junction is formed here, right, and this is P silicon, right, and then this automatically become N silicon, right. This is metal electrode fingers which are holding the cell. Now, how this this screen, the entire screen, it is painted with a paste with having 70% silver, organic binder and sintered glass. So, that you must have seen on the solar cell there is a transparent coating. So, it allows the solar radiation to enter to pass through the coating, so that through the photovoltaic effect the energy is generated. The back side is spray coated with aluminium spray printing, spray coating. So, this side is opaque and we do not require this side also. We for power generation we are concerned with this side only. Now, this cell is placed in a furnace. This after these coatings, 70% silver coating at the top and the bottom, this cell is placed in the surface at 600 to 700 degrees centigrade. So, what happens, the metal paste it diffuses into the wafer, connectivity is established. Metal when metal paste when it is diffused to the wafer, the connectivity is established. So, there is no any resistance for the flow of the current. So, there is anti-reflection coating. You must have seen these cells are normally black in color. So, anti-reflection coating is also done. It is done with the silicon nitrate or titanium dioxide, and the thickness of the layer is approximately 1000 angstrom or 10 to power 1 micron, right, and this completes the cell. Now, output of the cell, a cell, if you make a cell with this silicon wafer, it develops approximately 0.5 to 0.7 volt DC, and current density is 20 to 40 milliampere per centimeter square. So, nowadays amorphous cells are also used, multi-layer amorphous cells are also used. The single crystal cell was the basic cell to understand the functioning of photovoltaic cell. The amorphous cells are also available, they work more efficiently. The cell must be made of the material that it should be able to absorb the energy. We cannot go for any material. The semiconductors are the best material for making a solar cell, right. And as you know, the photon which is coming from the sun, it has certain energy and the energy is h nu. Nu is the frequency of photon. If we do not know the frequency, then C is equal to h nu, C is equal to light speed. So, nu is equal to C by h. Now, if you use it here, then energy is equal to Sc by lambda. For a particular light or wave, we know the value of lambda. So, if you want to estimate the lambda or the frequency, we like to estimate the value of lambda. Now, C is, you know, that 3 into 10 to power 8 meters per second. This is the speed of light, H is equal to 6.62 into 10 to power minus 27 ergs second, or let us be in SI system, 6.0 into 10 to power minus 34 joule second, right? And then if we take the output in electron volts, right? So, electron volts output will come is equal to 1.24 divided by lambda. 1 electron volt is 1.6 into 10 to power minus 19. This is the voltage of potential of 1 electron, charge of the 1 electron. So, E is 1.2. This is the simplified form. Simply when we know the value of lambda, we can find the value of E. Now, suppose there is a photovoltaic cell and rays of sun are incident on it. Diffuse radiations are also coming, direct solar radiations are also coming. Now, in a semiconductor, there are two types of bands. One is conduction band, another is valency band. In valency band, the electrons are, I mean, lowest level, lowest energy level, lowest energy level. Here the electrons are on high energy level. So, this semiconductor can be made of silicon, cadmium, telluride, gallium, arsenide. They are one, cadmium telluride and gallium arsenide, or silicon, or any, I mean generalized crystal I am talking about. Now, electron here, they are very stable because it is in a low energy level. Low energy level does not mean that it is unstable, it is quite stable, quite packed. And here it is on high energy level. So, little energy will be required here to excite the electron, high energy will be required here to move the electron. And the difference between this conduction band minimum energy in the conduction band, this is the minimum energy electron and this is the high energy electron. So, in the lowest energy levels there will be some electrons which are on high energy. In lowest energy level there may be certain electrons which are relatively on high energy. In conduction band there may be some electrons which are at lower level energy. Now, this gap, energy gap, is known as Eg, band gap energy. Now, why we are taking this as band gap energy? This is because the gap cannot be less than this. Highest is the minimum value and lowest is the highest value. So, this is but we cannot go, so band gap energy cannot be less than this, right. So, Eg is the band gap energy. Now, the photon which is coming on this cell should have E greater than Eg. In that case, the electron from the valency band will be ejected. When the electron is ejected, the hole will be created. So, electron will go to the conduction band. So, this will become negative and this will become positive. Now, this hole and the electron, they are free to move from outside circuit. So, a outside circuit will be made. So, there is a junction here, a junction will be here. So, P type and this is N type, right. This is front side, this is external load and this is the back side, it is connected, right. And this is how the current is current move in the load in this type of photovoltaic system. Now current which is coming to the cell can be simplified. If you draw the diagram, it is something like this. This is short circuit current. This is your semiconductor device. This is common equivalent circuit is going to be like this. R shunt, R series, R load, and this is voltage. Because this resistance of shunt and resistance of series is very low, it is not very high. So that is why we can do away with them, and if you want to have short circuit current, then this is nothing but Ij and this is I, and here is the voltage. Now, if you look at the characteristics of the PV cell, because any device we use, we have to, well converse with the characteristic of the device as well. So, if we draw current and voltage for PV cell, then current, voltage will vary from 0 to 0.8. Let us say current in ampere, it is going up to 1. If we keep on changing the voltage, let us say this is 0.2, 0.4, 0.6 and 0.8 volt DC. So, short circuit current, the current will remain constant. We keep on, so it works in a different way from a resistance. Because in resistance, if you keep on increase the voltage, the current will automatically increase. But in semiconductor, it will not happen. The current will remain constant for certain voltage, and then there is a sudden breakdown. And this breakdown is approximately near 6. Right? So, from 0, if you start with 0.2, 0.4, 0.5, the current is fixed. It is approximately, let us say, 1. But when you cross certain voltage, approximately 0.6 or 0.56, there is a sharp drop in the current. This is for short circuit when there is no load, right? But when you want to draw the power, when you are drawing the power, then it will follow up to certain extent, it will follow this Ohm's law, and straightway it will go up. And then again, after attaining a peak value, it will come down. Now, when it is coming down, this is the peak value, and this current is Im, and this is Vm, maximum current, and this is maximum current at maximum voltage. The current at maximum voltage is Im, otherwise maximum current is this, but we are taking current at maximum voltage. So, there is a relation. I current is equal to ISC short circuit minus IO exponential EV over KT minus 1. This is the equation. IU is reverse saturation current. E is the charge of the electron, that is 1.602 into 10 to power minus 19 joules per volt. K is Boltzmann constant, it is 1.381 into 10 to power minus 23 joules per Kelvin. T is temperature, in Kelvin. ISC is short circuit current, right. So, for that case we are getting this formula. So, for any moment we want to find I, we can use this formula. Now, when there is short circuit, I is 0. When there is short circuit, I is 0, and when this I is 0, then with the help of short circuit current we can find the value of V. So, V short circuit or open current, open circuit is going to be equal to kT by E natural log ISC by IO plus 1. Now, V is known to us, then P is equal to power developed is equal to V into I, right. Now, in any device, power is V into I. Now, I, we can again take this short circuit minus IO exponential of, exponential of EV by KT minus 1 multiplied by, this is current multiplied by V, and this is power. And if you want to find the maximum power, we should differentiate with respect to voltage and put it equal to 1. Maximum power at what voltage? And when we do that, we get the expression 1 plus EVM by KT exponential of EVM by KT, and that is equal to 1 plus, that is the condition for maximum power, and this gives the maximum current as EVM by KT Once IM is known, we can go for the maximum power as, now EV, this will be multiplied, this EVM will be multiplied by EVM square. So, multiplied by EVM again and VM again, that is it. Now, this will be simply multiplied by VM. So, when this is simply multiplied by VM, the VM will, it will become VM square, and we will get this for the maximum power. So, this is how we can calculate the maximum power from any PV system. Now, the efficiency, maximum efficiency, the maximum efficiency is going to be the maximum power, maximum voltage divided by IT and AC, and this is equal to IT is the total solar flux and AC is the area of the cell, right, and this will give you the maximum conversion power. Now, there are different type of solar cell, they are known as the common solar cells. Single crystal silicon, we have already discussed single crystal silicon, multicrystalline, silicon, third is amorphous silicon, fourth is cadmium, fifth is copper, gallium, dieselenite. So there are 5, there can be other also. Now, the use of solar cell in the society is increasing. In the individual persons, they are putting solar cell in the rooftop, and they are using this energy for different lamp appliances. But the cost, major cost is coming. Cost is not coming from the solar cell, it is coming from energy storage. Now, throughout the world, there is a hot research topic, how to store the energy. Right? If we are able to store energy at the low cost, the cost of the solar PV, the power generation will drastically reduce. And the benefit of this type of power is we can have this type of energy at the household level, and we can go for the mega plants by putting solar panels on the field. It, because the power intensity is low, per meter square is low, so a lot of area is required for solar power generation now. And this is and this panel, these panels are using the fertile land. So now the ideas have come, instead of putting on the ground this solar panel, they are put on the columns of the height of 20 or 25 meters, so that the fields or the fertile land can be used for the agriculture purpose. Because these type of cells, they do not require any high order of maintenance. Only cleaning is required. A lot of work is going on the cleaning of the solar PV also. There are many ways. I mean, you can just wash with the water, right? Nowadays, people are trying to develop the micro robots which can clean the uh, solar panel. The micro robots are like bugs. So, they will be traveling on the solar panel surface, and the solar panel surface will be cleaned. So, there is a lot of scope of work in the area of cleaning of the solar panel and installation of the solar panels. And now the energy developed in the solar panels can be used in many ways. You can use this for a domestic purpose, and you can have a, I mean, an energy, zero net energy locality or zero net energy building, or this energy can be directly connected to the main grid. That is also possible. So, when this energy, in that case, you do not have to, store the energy. So, this energy can be sold to the companies which are supplying the electricity, and this DC, then converter is required. So, this DC, which is energy which is coming from the solar cell, it will be converted into the AC with the help of a converter, and it will directly go to the grid. But this conversion process, the efficiency of the conversion process is not very high. So, that is why it is always recommended that where you generate the solar energy, you consume it there itself, until unless it becomes necessary to transmit this energy to the grid. That is all for today. Thank you very much.